Application of AC bridges. Let's discuss regarding de Sauty's bridge. This network is used to determine the unknown capacitance. Typical de Sauty's bridge network is shown in figure 2.4. This is a simple modified form of Wheatstone's bridge network driven by an AC source. In the experiment, one of the resistances or one of the capacitances is varied, keeping all other values fixed to achieve balance condition of the bridge for AC. In figure 2.4, D is the current or voltage detector, galvanometer, or it's the sensitive voltmeter. In the experiment, either C1 or C2 is varied to determine the value of the other capacitor in the network. From the basic meaning of balancing of the bridge, we have Z1 by Z2 is equal to Z3 by Z4, where Z1, Z2, Z3 and Z4 are the impedances of the four arms of the de Sauty's bridge shown in figure 2.4. Equation 1 may now be written as 1 divided by j times omega C1 whole divided by 1 by j omega C2, which is equal to R1 by R2. This implies C2 by C1 is equal to R1 by R2, or C2 is equal to C1 times R1 by R2. Thus, by knowing the values of R1, R2 and C1, the value of C2 may be determined by balancing the de Sauty's bridge. Let's now discuss regarding Robinson's bridge. Usually, Robinson's bridge is used to determine the frequency of the AC source that drives the bridge. Typical form of Robinson's bridge is shown in figure 2.5. In the experiment, usually the resistance in series with C2, that is R2 in figure 2.5, is kept fixed, while all other values are varied to balance the bridge. While balancing the bridge, R1 is taken to be equal to R2 for convenience of calculations. From the basic meaning of balancing of the bridge network, we have Z1 by Z2 is equal to Z3 by Z4, where Z1, Z2, Z3 and Z4 are the impedances of the four arms of the bridge network in figure 2.5. Equation 3 may now be written as 1 by R1 plus j omega C1 whole to the power minus 1 divided by R2, which is equal to R3 plus 1 by j omega C2 whole divided by R4, or R1 divided by 1 plus j omega C1 into R1 times 1 by R2, which is equal to R3 minus j by omega C2 divided by R4. Or this can be rewritten as shown. Therefore, R4 by R2 is equal to R3 by R1 minus j by omega C2 R1 times 1 plus j omega C1 into R1. R4 by R2 is equal to R3 by R1 plus R3 j omega C1 minus j square omega C1 into R1 divided by omega C2 into R1 minus j by omega C2 R1. Therefore, R4 by R2 minus R3 by R1 minus C1 by C2 is equal to J times R3 omega C1 minus 1 by omega C2 into R1. Equating the real and complex coefficients on both the sides of the equation to 0, we obtain R4 by R2 minus R3 by R1 minus C1 by C2 is equal to 0 and R3 omega C1 minus 1 by omega C2 R1 is equal to 0. Therefore, R4 by R2 is equal to R3 by R1 plus C1 by C2 and omega square is equal to 1 by R1 times R3 into C1 times C2. In the experiment, for convenience, if we set R1 is equal to R3 is equal to R and C1 is equal to C2 is equal to C, then the above equation reduces to a simple form. R4 by R2 is equal to 2 and omega is equal to 1 divided by square root of R square C square. Or R4 by R2 is equal to 2 and frequency F is equal to 1 by 2 pi times square root of R square into C square, where F is the frequency of AC source that drives the bridge network. Thank you.